Okay, so use the precise definition of limit to show that the limit as, for this one, it's as x approaches 1, of x squared minus 1 over x minus 1 equals 2. So let me go through that really quickly. This is very similar to the ones we did on the exam, but there is, I think a very real difference here. So let's see where that comes up. All right, so first we have the finding delta portion of things. So I want to start off with f of x minus L less than epsilon and work towards x minus a less than delta. Here, in this case, a is 1. Okay. My f of x is x squared minus 1 over x minus 1, and the L is 2. Okay. So what I'm going to do is I'm going to factor this. X squared minus 1 is x plus 1 times x minus 1. And I can cancel these, but I'm not in a limit, so I can only cancel these if x is not equal to 1. Okay? So when I make my, these are equivalent statements, this is going to be equivalent to x plus 1 minus 2 less than epsilon, provided x is not equal to positive 1. Okay. And then 1 minus 2 is a negative 1. Okay, so we're going to pick delta equals epsilon. So now on the logic side of things, for any epsilon greater than 0, let delta equal epsilon. Then if 0 is less than x minus a is less than delta, we have 0 is less than absolute x minus 1. So x is not equal to 1. And we have that x minus 1 is less than delta. So x minus 1 is less than epsilon. And I know that if x minus 1 is less than epsilon, I can just follow my train back up. So that tells me that f of x minus L is less than epsilon because I have this extra piece now. So the limit as x approaches 1 of x squared minus 1 over x minus 1 is equal to 2.
Okay. So for the for that step where you say that if x can't be equal to 1, you can't do that. You technically can't do that math because it's not in a limit. So you have to like actually mention that in this question, right?
Yeah, because these two expressions are not equal when x is equal to 1.
Yeah.
So they're only equal for the x values that are not equal to 1. So, if I want to make this logical jump, I have to make sure that I'm cutting that out, because here it doesn't look like there's any problem with 1.
Yeah. Okay, so you have to okay, so you have to clarify that in this one.
Yeah.
Actually, can you explain like the logic section again?
Sure. The whole reason that we go about that is because when I look at the definition of the limit, right? If I let me write this out. The definition of the limit that we had is that the limit as x approaches a of f of x equals L means that for any number epsilon greater than 0, there exists a number delta greater than 0 such that if 0 is less than absolute x minus a is less than delta, then absolute f of x minus L is less than epsilon. So what we want to do is, in order to show this limit, we have to show this definition, right? We have to show that it's satisfied for this particular situation. So what we need to do is start with an epsilon greater than 0 and then show that there is a delta by writing down what it is. Okay, and then if we have this first statement, then we get the second one. But what we did here is we sort of worked backwards, right? I'm not saying if x minus a is less than delta, I'm starting with f of x minus l less than epsilon. So I'm working backwards, and that's the problem. So what I need to do is sort of reorder it and say, okay, well, from the beginning, I would say, if you have an epsilon, pick delta to be this thing, and then if you have the if statement, then that gives you f of x minus l less than epsilon. That's what we wanted to show, so we have the limit. Okay, so the problem was that when we want to find delta to actually do the work, we have to work backwards. So to write it in a way that makes sense, we have to, start from the beginning, not from the end.
Okay, but that's okay. So for any epsilon is greater than let delta equal e, that's true because we found that x minus 1 is greater than delta, and then we kind of made that equal with the epsilon one. So that's why delta and epsilon are equal.
Yeah. In this case, they're equal. Like some of them we had, like maybe it's epsilon over 6 or it's something like that.
Okay, then. So then, yeah, I get the then if part. So then after that section where we say we have 0 is less than x minus 1 or x, yeah. That is mentioned like
So we're saying if this happens, right, if you're assuming 0 is less than x minus a less than delta, then what I'm going to do is I'm going to split off this first portion and say, well, I'm assuming 0 is less than x minus a, so that's 0 less than x minus 1. That means that x is not equal to 1, right? And then I look at the other side of things and I say, okay, this is also saying that x minus a is less than delta. So this statement is really saying two things. It's saying 0 is less than x minus a. It's also saying that x minus a is less than delta. So I'm just writing those as two separate things. If 0 is less than x minus a, that means that x is not 1. And if x minus a is less than delta, that means that x minus 1 is less than delta, right? And I can continue on from there, right? Since delta is equal to epsilon, that means that x minus 1 is less than epsilon. And then following my steps backwards, I get f of x minus l is less than epsilon.
okay. Okay, yeah, that makes sense. Well, thank you so much.
Okay, sure.